Approximately 1 in 4 Americans over the age of 65 report falling each year. This leads to high medical bills along with decreased health and well-being. To solve this problem, we built Soteria, an exoskeleton that prevents users from falling by ensuring that they maintain a balanced gait during walking. Current strategies to help solve this problem involve passive systems, such as handrails, walkers, and canes. Unfortunately, these passive systems do not provide the same versatility, ease of use, and seamless integration as active balance correcting systems, such as our exoskeleton. In simulation, we demonstrated the feasibility of providing torque at the hip to maintain stability. First, we simulated normal walking with a neuromuscular model. We then showed the impacts of decreased muscle strength that is common in the average elderly population, and that this can lead to instability. Finally, we added PD control that provides torque at the hip, and we were able to show that the model remains stable and does not fall.
Over the past year and a half, we have developed a fully functional hip exoskeleton prototype that is able to predict optimal hip angles and actually to enforce optimal walking behavior on the user. In our validation tests, we have shown that the system is able to reflect optimal walking patterns in regular walking gait as well as when the user undergoes large perturbations. In our first demonstration, we will show a user wearing the exoskeleton and walking normally in a straight line. As she is walking, the exoskeleton is constantly estimating her gait parameters and actuating her thigh to the optimal angle at every step. In this graph, you can see that when the exoskeleton recognizes that the user is lifting her leg off the ground, at this point it sends an actuation command for the exoskeleton to move to the calculated angle. You can see that when her leg lands back on the ground, the commanded angles and her actual hip angles are at the same value. In the second demonstration, we will be showing how the exoskeleton reacts when the user undergoes a large perturbation during her gait. The user starts off walking normally. In the middle, she is tugged to cause a perturbation to her step. Her reaction was to step her leg out to the side, catching herself successfully. The exoskeleton also came to the same conclusion and abducted the leg, reflecting the successful recovery maneuver that the user instinctively performed. In this graph, you can see that when she is perturbed, the abduction angles of the user's leg and the exoskeleton's commanded angles exhibit the same behavior. Now let's dive further into how our system works. We have sensors that are mounted to our mechanical frame, which feed data to our software subsystem. Our processing subsystem takes in this information and estimates the current gait parameters of the user. It uses these parameters to determine what commands to send to the actuation subsystem. The actuation subsystem then uses these commands to handle low-level controls and actuate the leg.
So building the actual exoskeleton hardware was a big part, but also a really fun part about the project. We custom built our exoskeleton frame by using aluminum for the backplate and actuator housings, as well as 3/4 inch PVC pipe for the linkages. We also assembled our actuators ourselves by coupling drone motors with a 2-stage planetary gearbox and attaching encoders to them. So when you work with robots that interact this closely with humans, safety is an important factor which needs to be incorporated in every stage of the design process. In order to do this effectively, our exoskeleton has mechanical hard stops to limit the range of motion of the user's legs, an emergency switch to cut power if the user feels any sort of discomfort, and similar limits in software as well. During testing, we also had access to a really great harness system that can secure the user and prevent them from falling in case of any issues. Another important part about our hardware is our electrical subsystem. So we have a circuit board that takes in a 48 volt and a 12 volt power supply and powers all the electronics on board. This includes the motor controllers, the sensors, and an onboard computer. We also incorporate a power dissipation circuit which safely dissipates back EMF that the user generates when back driving the motors. It does this by identifying when the user's legs are driving the actuators backwards and then engaging brake resistors to dissipate this energy.
Our exoskeleton has a sensor suite that enables us to estimate the gait parameters of the user wearing it. The sensing subsystem comprises of two IMUs placed slightly above the knee, specifically at the distal femur. We also have encoders attached to the motors to provide feedback to our controllers. Additionally, we have IR sensors attached to the feet that provide us with the ground truth of the leg's swing or stance state. Our software stack is developed in C++ and Python, and it runs on ROS. The data from the IMUs are used as features along with the ground truth from the IR sensors in order to train a machine learning model that predicts whether the leg is in swing or stance. This is mainly a design decision to build a system that extends to the knee instead of the feet. Our exoskeleton is based on the linear inverted pendulum model. For the LIP model, there is a unique capture point corresponding to each state, which is essentially a point on the ground where the person can step to retain balance. An important parameter for this model is the center of mass velocity, and we compute it by sensing velocity at the knee from the IMU and extrapolating it to the center of mass. We compute the forward and lateral capture based on the model and obtain a desired hip angle that the exoskeleton must actuate to. We also estimate the duration of the swing of the next step based on the previous steps, and this information, along with the desired landing angle, is fed to our trajectory planner.
The planner takes the estimated hip landing angle as the goal and the estimated swing time as the time to reach the goal. To design the shape of the trajectory, we refer to a curve from vintage datasets, which is the hip movement of humans normal walking. We scope the trajectory according to the landing angle at the swing time. After that, we perform a phase shift to pre-feed the trajectory to make it actuated fast. After that, we feed the trajectory to the actuation subsystem. The actuation subsystem takes the desired position command as the input and actuates the motor to move the leg link to follow the desired positions. We use two Robotech controllers. Each of them actuates one flexion extension motor and one adduction abduction motor. The controller takes the position feedback from the absolute encoder and perform PID control to send a command to the motor. For safety consideration, we limit the current as well as the PID gains.